Yes, he is.
Wow, okay.
Good job, guys. Okay, quick, just review of yesterday's topic. All right, so we talked about Extrema yesterday. And we broke that down into 3 categories, just to kind of summarize. And this is how you can think of them. Relative extrema, we said, are just topological features. Peaks are relative maxima, valleys are relative minima. Absolute extrema, we haven't really talked a whole bunch about those. We're going to look at those today. Those just mean the highest and lowest points on some interval that we define. And then global extrema are just the highest peaks and the lowest valleys on the entire function, right? Critical numbers, we know that all peaks and valleys, all relative extrema, have to occur at critical numbers. And there's only 2 places where those can be, and they're both related to the first derivative. Where the first derivative is 0. And what's, do you remember, or does this make sense? What kind of a peak and a valley do we associate with this kind of a critical number?
Horizontal.
Again, it's a horizontal tangent line, right? And so what's the kind of the character of that kind of a, oh good, it's a rounded, good. So this would be like a rounded peak or a rounded valley, good.
Quick question.
Yes?
It wouldn't be the same if it was a cusp, would it?
No, a cusp would be where it's undefined.
Okay.
Yeah, where it's undefined, where you get a sharp corner, you can get a peak, sharp peak, or a sharp valley like that. Okay? Now, are all critical numbers guaranteed to give you peaks and valleys? No, you gotta check them. Our strategy is pretty simple. We're just gonna locate the critical numbers and then test them all and see which ones work out to be peaks and valleys and which ones don't. And we looked at a couple of weird examples of how you could get stuff that, false alarms, right? Okay, so let's take a function and let's just practice this. To me, this is really a fun part of calculus. This is where you get to actually get in and do some interesting stuff. I'm going to show you a really cool way to visually represent all this stuff in a table too. And this is going to take us, we're not going to get a lot of this done before break, but we'll get just a little bit of, get you thinking about it a little bit. Let's take the example, how about, I'll just take one out of the book here. We'll end up looking at a lot of these, but let's just start off with this one. Let's just take f of x equals 3x to the 2/3 minus 2x, how about it? Let's take that function and let's do 3 things. First of all, let's find all the critical numbers. Let's find the relative extrema, and then let's find the absolute extrema on an interval. Now, I wanna just, I'll be real honest with you about this. When we're finding relative extrema, the way that we're doing this right now is, in mathematical terms, pretty dorky, and it's not what we're going to do eventually. It's really not the best method. I'm going to show you there are 2 much better. Thank you. There are 2 tests that we have called the first derivative test and the second derivative test that are much better and more efficient than how we're going to look at this today. But I think it's still worth just kind of, before we get into those, maybe looking at even just a single example, showing that we can represent this, even with the calculus we know right now, we can represent this function and understand it pretty well just by the little bit of calculus that we even have at this point. So let's take a look at this guy then. So if we're going to find the critical numbers, what do we have to do with that function? Got to take the derivative, right? So this is all calculus stuff. So first derivative, what do we get from the first derivative of this function? 2x. Okay, good. 2x to the, good. Does that make sense? Negative 1/3, right? Minus 2, okay? So there's our first derivative. Now, what do we do with that? I mean, where are we got to find the critical numbers. Well, they're both instances are related to that first derivative. Okay, we're gonna set it equal to 0, good.
That's
So-
the 2x to the negative 1/3, that goes to 5.
Good, and that's a good idea. Let's go ahead, and whenever we get negative exponents, let's write those as fractions with the variable on the bottom. So we could write that as 2 over x to the 1/3, which is really just the same thing. If you'd rather, it doesn't really make any difference, but you can also write that as a cube root.
Would be negative?
No, all the negative, what does that negative exponent mean?
It just goes to the bottom.
Goes to the bottom, yeah.
Put the negative.
Oh, and then we get the -2 over here, yeah, then we get the -2. Good, okay? And so, we can set this equal to 0, and that's one test we're gonna do, right, and solve. Okay? So how do we solve this equation? We're gonna do a lot of this kind of stuff, solving equations, because we're always gonna set the first derivative equal to 0 and solve. So your algebra is, you're gonna get more practice. What would you do to isolate that x? There's a lot of ways you could do it. What's a good easy way though?
2 over.
Okay, good. How about if we add the 2 to the other side? And really, that's the same thing as 2 over 1, isn't it? Now, it's a little bit inconvenient that x is on the bottom, but how do we typically solve ratio equations? Cross multiply, yeah. And there's a good trick, I'll show you. We cross multiply and then divide. You can do that in one step. I can't remember if I showed you this, I'm sure you've seen this at some point. But whenever you have a ratio set up like this, a ratio equation, you can always exchange elements diagonally. That's just combining 2 steps. You guys know that trick? Okay, so we can just do that. If we do that, we end up with, what do we get? We get the cube root of x by itself on one side. Let's go ahead and flip it over to the left, how about? On the other side, we just get 2 over 2, which is 1, yeah. Okay, and now, what? Okay, cube both sides, good. So if I cube both sides, I get x equals 1. Okay, remember though, when you take both sides of an equation to a power, do you remember any danger zones going on? This would have been back in honors algebra 2, you would have probably spent a lot of time on this. No, not plus or minus, but there's something else that happens. Whenever you take both sides of an equation to a power, you run the risk of introducing extraneous solutions. Do you remember that? And let me give you just a quick separate example, okay? We'll jump right back to that problem, but what if we had something like, let's say, negative the square root of x. How about this one? Never mind. How about if we do, that's not what I want to do. What if I had square root of x equals negative 1? How do I solve for x? I mean, by there we square both sides, right? So I'd get x equals 1, right? Is that a true solution? It's not, is it? If I plug that back into the original equation, does it satisfy it? No, it doesn't, right? And so, in this case, the extraneous solution that we introduced is a non-solution. It turns out there aren't any real solutions to this, are there? It's imaginary, right? So there are no real solutions, and when we checked it, we found out that the one that we got doesn't work. Does that make sense? Do you remember doing that stuff? Okay, good. So here, it's gonna work this time. If I try, we get 1 for an answer. If I plug 1 back in there, yeah, the cube root of x is 1, isn't it? So, yeah, makes sense. So 1 is one critical number, right? So we'll collect our critical numbers up here. Find the critical numbers. Well, x equals 1. That worked. Okay, what other work do we have yet to do on this one? Okay, where it's undefined, okay? Now, if we go back up here, and this part right here is really just f prime of x, right there, isn't it? Okay, we don't need to set it equal to 0 for this second task, but we need to take a look at that function and analyze it. Now, where did we say yesterday, just remind me real quick, where is it that a function could be undefined? For x values where what two things happen?
Zero raised to fraction.
Okay, good, divide by 0 or even root of a negative number. Okay, so do we have any even roots in this function? No, it's an odd root, isn't it? Okay, so we're okay with that, we ducked that bullet, but there is potential for this thing to have a 0 on the bottom, isn't there? Now, where does that happen? Well, it looks like right there, right? Okay, the way I would urge you to kind of think about these is when you look at the function, just kind of identify the parts of the function that could cause that to happen and only focus on those. So in this case, we know that here's the part that could go to 0, right? And so we have to find all, and this is pretty easy, you can see the answer pretty obvious there, but I still want to take you through and show you how you can, for a harder problem, you can apply the same strategy, and it's very useful. Everything in the green bubble is where we could get a 0 on the bottom. It's the only place though, right? So then we'll go up here and we'll look at, we'll do a non-equation. We want to know, when is the cube root of x not equal to 0? Because those are the places where we're going to get critical numbers, right? Those are the places we need to exclude. You could just as easily make that an equal sign. In fact, let's do that. Maybe that it might seem more, might seem a little weird. Not equal to, but you could. Algebra works the same for a not equal to sign as it works for an equal sign. So what do I do this time to solve? Well, cube both sides again, right? So I just get x equals 0. If I plug that back in, it works, right? And so x equals 0 is the place where everything in the dangerous green bubble went to 0, right? Does that make sense? But we don't have to focus on the rest of the function. That's the only part we're interested in, right? So that's our other critical number. We get critical numbers at x equals 1 and x equals 0. Make sense? So if we're looking for relative extrema, where do we look? X equals 0 and x equals 1. That's the only two places it could possibly happen, right? So on this, it's kind of boring. If we go now, let's go see what happens at those places. We're going to make a table, and we'll expand on this table later. But for now, it'll be pretty limited. Okay, so there's our function, or our derivative of our function. Let's write the original function up here too. Let's see, we had f of x equals 3x to the 2/3 minus 2x, good. Okay, so if we make a table here then, let's set up our table like, oh my gosh, let's do that. In fact, I'm gonna go ahead and do that. Put the x down here. This is our x row. This is f, and that's f prime. And eventually we'll add an f double prime to that also, second derivative. So the critical numbers were at x equals 0 and x equals 1, right? And we had in our first derivative category, here we had an undefined, and here we had, isn't that right? And then this was a 0 first derivative, right? Okay, so we know those are our critical numbers. For now, we just kind of just barely got up to this at the end of class yesterday. We know that if we were to graph this function, we know that those are going to be the places where potentially we could get those peaks and valleys, but those are the only places where we could get peaks and valleys, right? So we can kind of divide this thing up into sections. So between those, on those intervals, we want to maybe test some points. Okay, so now you guys talk to me about this. That takes us up to where we were yesterday. See if we can push this a little further. So if we wanted to get a sketch of this graph, what could we do? Any ideas? And here's our function in case we want to put any points back into
what you get.
And this isn't horribly different at this point from how you would normally sketch a graph. Going back into your past, you would have probably, absent a graphing calculator, you would have probably just made a t-table, right? Okay. The nice thing about this is now, with our analysis, we may not need to have so many points on our t-table as we used to. Okay, and it turns out that in our very near future, within like a week of class time, we'll need like only 2 points on our t-table, and that's it. And then the rest we can just fill in from calculus. And we're not trying to make an exact graph, we're just doing a sketch here, right? So what would be maybe the first obvious points that we might want to check the value of the function at? 0 and 1, why not? So if I plug 0 into my function, what do I get back? 0. Okay, so first of all, if I do this, you see that this really looks like an ordered pair, it's just written vertically. Okay, so we get, there's a point at 0, 0. If I plug in 1, what do I get? 1. Everybody agree? Okay, so I plug in 1, and I get back 1. So if that's 1, we're right, or I guess that's 1. We're like right there. Okay. Where could I maybe test some values now? -1, okay. If I plug -1 into my function, what do I get back? What is -1 to the 2/3? It's 1, isn't it? What does that mean, -1 to the 2/3? Well, typically you'd cube root it and then square it. So what's the cube root of -1?
1.
Negative 1, right? And then squared?
1.
1 times 3, and then minus 2 times -1. 5. So it's up here pretty high, isn't it? So at -1, we're clear up here somewhere. So what does that tell you about this critical number right there? It's a minimum, isn't it? Are we sure that's enough information? I mean, maybe it is. I'm just asking you. Because why or why not? And this is an interesting discussion. This is kind of. Say it again. This one's. Say it again.
Is at 1.
This is at 1, 1,
But
yeah.
that's at -1, 5.
And this is at 0, 0.
Yeah.
And this is at -1, 5.
Yeah, so it is less than
Okay, if it were, right. And we know it's not, but if it were, yeah. Can this thing, is there any possibility to the left of this point that it could ever dip below that again?
No. Yes.
How come?
Well-
Elizabeth, how come?
It's the only relative extreme.
Aha, okay. If this thing, in order for this thing, just makes sense, in order for this thing to dip down again, what would we have to have?
Another,
You'd have to have a peak there, wouldn't you? Right? Does that make sense? If the function going from right to left here is gonna increase like this, if it were ever gonna turn around and come back down, there would have had to have been another peak there, right?
Oh.
Does that make sense? And so now, to us, relative extrema, aka peaks and valleys, not only are they interesting features, we also recognize them as turning points on a graph, right? That the graph, it can't turn without a peak or a valley, unless there's some kind of vertical asymptote there also. That's the other place where vertical asymptotes are like separate universes on a function. You get a vertical asymptote, what's going on this side and this side can be utterly disconnected. But we don't have any of those, do we? Right? In this function. We don't have any vertical asymptotes. So this thing can't turn around. Right? We know that it's gotta just do that kind of thing forever on that side. Okay? Now this point is higher than this point, isn't it? Between these 2 points, could this function ever turn?
No.
It can't, because we only have 2 critical numbers total. So the maximum number of peaks or valleys we could have is 2. 1 there and 1 there. So this function has to do something like that. What the exact shape of the curve is, we don't really know and probably don't really care. But does that make sense? Okay. So then, we only really need one other test point. We didn't even need one in between here, did we? Okay. Other one just might be out here somewhere. Does it even matter which point we take it at? I mean, not really, does it? Let's pick a convenient one. How about if we pick something like, I might pick something like 8. How come? It's a big number, yeah.
Just to see if it's high or low, so you know there's.
The cube root of 8 is 2.
There you go, bingo. Yeah, 8 might be a good one because the cube root of 8 is 2, right? So if we pick a value like 8, the cube root of 8 is 2, squared is 4, times 3 is 12, minus 2 times 8 is 16. So that's negative, isn't it, right? Okay, so then if out at 8, we're way down, pretend 8 is just out here, we're way down here. I drew that wrong, didn't I? What does that really need to be?
Keep going.
Well, it needs to be, this one needs to be, and I actually drew this, which one did I draw wrong? This one, this is undefined.
Yeah.
Yeah, so I drew that, what shape should that have had?
Corner.
Should have been a corner, and I would have known that, because that's undefined, that sticks out to me as being a jagged topography, right? So I gotta redraw this thing. I didn't do a very good job of drawing this curve. Let's go back. Is that gonna?
Sure.
It is. There we go. Let's try this again. So this one should probably do something more like this, right? It's got the jagged. This one's gonna be horizontal though, isn't it? This is a horizontal tangent. So we know that we can put a horizontal line there next to that 0, which reminds us that it's a flat curve. And this one's gonna go. Okay. So that is not perfect. We didn't mean for it to be perfect, but it's an accurate sketch of the behavior of that function. Okay? That makes sense? Okay? All right. So what if we change our problem just a little bit though? What if we say now, find the absolute extrema on the interval from -2 to 2? Inclusive.
Restricted to that.
Yeah, it's just restricted to that one area. What does that mean in terms of our picture? Well, if we go over to our picture now, that's like saying we are just going to take a knife and we are just going to cut out a section of this thing, right? So we're going to go back at -2. We're going to make a cut up here like that. Over here at +2, we're going to make a cut like that. And we're just going to cut out this section, and only the stuff inside the purple square is what we're interested in, right? And all we want to know here is that for an ant walking on this function, on that interval, where is the highest point that he gets to stand and the lowest point that he gets to stand? Now, where are the candidates? Where would be the candidates for the highest and lowest point? Just sort of qualitatively.
2 and -2.
Okay, 2 and -2. And just in general, I mean, what if I didn't draw this to scale? See, we don't know that I have drawn it to scale. So where are the possibilities that we might want to look for the highest point? Okay, so at this end point, right? Because wouldn't you agree as he walks backwards, he's always walking up, so he's gonna get to his highest point walking up this curve when he runs into his boundary, right? But the other candidate would be right there, wouldn't it? Because there's a peak. Where are the candidates for the lowest point that he's gonna get to walk? Okay, that would be there, because that's a valley, or over there, because that's an endpoint. So in general, when we're looking for absolute extrema, where do we look? Endpoints or peaks and valleys, right? But because if you were just looking for the absolute extrema, would we even have necessarily had to determine if these were peaks and valleys? Once we found where the critical numbers were, there's only going to be, in this case, 2 critical numbers, right? They may or may not be peaks or valleys. If we're just trying to find the absolute extrema, couldn't we just say, well, let's just check the values of all the critical numbers and the endpoints? Doesn't that covers all our bases, doesn't it? Does that make sense logically, that's a little bit less work? Right, because we know that if it does so happen, that a peak is the highest point on that interval, well, it's gotta be a critical number, so we will have checked it. Does that make sense? If it turns out a valley is the lowest point, that also has to happen at a critical number, and we're gonna check those. If it's an endpoint, we'll get those too, right? So really, all we gotta do for finding absolute extrema is just find the critical numbers, find the endpoints, fill in this row of our table right there, and see which has the biggest functional value, biggest Y value, and which has the lowest Y value, and those are the winners, right? The highest and lowest points. Make sense? Okay. All right, let's look at a couple pictures. I want you to tell me, based on this picture, does it have, tell me, does it have, and if so, where are the absolute maxima and minima? Okay. So let's say, okay, where is the absolute max, if there is one? At what X value? At A, okay. C, okay, if C is the minimum. Make sense? Okay, good. Let's change this a little bit. Does this change our answer? No? Okay. Does that change your answer?
Yes.
Yeah. What's it change?
Okay.
It's not A. Where's the absolute maximum now?
Just below.
Who passed it to the right, me? Okay, so what point then? How about if could I just pick that point like right there?
Yeah.
Okay. Anyone see a problem with that? Something seem a little bit iffy about that. Isn't that kind of like that example we talked about with the door earlier in your comments?
It's infinite.
Yeah, right? Because if I'm walking towards the door and I want to pick the closest point to the door without being at the door, couldn't I just increase the power of my microscope and find an infinite number of points still beyond that, between that and the door always,
Yes.
right? And so what do you think that tells you about the existence of an absolute maximum? There isn't one. Yeah, doesn't exist, does it? Right? Because there isn't a point that I could ever stand on and say, this is, the ant can't ever get there and say, aha, this is the highest point, right? There's always gonna be a small step you can take further, get a little bit higher, right? So,
Is,
yes,
if both of them are not filled in, would there not be an absolute minimum either? Or would it-
okay, well, would there be an absolute minimum in this case? Yeah, it's still at the bottom, isn't it, right? Now, what if I did, how could I change it so there wouldn't be an absolute minimum, maybe? Ah, yeah, what if I did something like this?
Okay.
Oops, you get the idea, if I did something like that,
Okay.
right? Does that make sense? Okay. What if I do something like that? Does that have an absolute minimum?
Yeah.
That does, doesn't it?
Yes.
In this case, the absolute minimum is right there. That's a solid point. And only, it's like the ant, there's like a one little drop in the function, but the ant, theoretically, an infinitesimally small ant could stand on that, right? Okay? All right, I think we're getting the idea of this stuff, getting the hang of it. Okay? Let's try maybe. So just try one of these on your own here. Let's try a trig function.
Matrix.
Oh, come on now.
Why do you speed read?
Okay, try that one. Well, I take roll.
Okay, we're gonna be negative one.
No, CC, it was a
Sign over cosine, right?
Cosine over sine.
changes that. They believed it.
Okay, we're getting close. I'd give you a little more time, except it looks like we're getting pretty close to the end here. So,
We have 8 minutes.
8 minutes.
So wouldn't it just be cosine over sine because they both have the same denominator?
Okay, good. We want to write it in terms of cosine and sine, don't we? So if we take the derivative, Campbell already told us that's negative cosecant x, cotangent x. In terms of sines and cosines, cosecant is,
Negative one over sine x.
okay, and cotangent,
Cosine x over sine.
so I can just do that.
Yeah. Oh, okay.
Okay. All right, so now if I want to find the critical numbers, right? Critical numbers, so. Critical numbers, let's find out, first of all, where is our first derivative equal to 0? Okay, so if this is my first derivative, agreed? If I set this equal to 0, where is a fraction equal to 0? No, just in general, where is a fraction equal to 0? When the top is 0, okay?
Yeah.
So, now do you see, if we've ever got a rational function like this, if we can write our derivative function as one big fraction, both of the critical numbers are related to the fraction. The zeros of the top of the fraction are where the derivative is equal to 0, and the zeros of the bottom of the fraction are where it's undefined, right? Does that make sense?
Yeah.
Okay? So then, for this one right here, f prime of x equals 0 when the top, negative cosine x equals 0. This is a really good habit to get in math. It's a really good trick. If we can take a complicated equation, and if we're looking for specific kinds of things happening, isolate the parts of that equation where they happen. I didn't say that very articulately. What I mean here is, we can just pick only where the top of this thing equals 0 and get an easier equation to solve, right? For the first derivative test, for finding out where, not first derivative test, finding out where the first derivative is 0. So now this is just a unit circle issue, isn't it, right? If we just slap down a quick unit circle,
Slap her on there. Slap her on down there.
Stare at it before you.
okay, so quick unit circle, where is the cosine equal to 0? Okay, good. Now that's the x coordinate, right? So that's going to be there and there on the unit circle. That represents, each of those represents an infinite number of places, each lap of the unit circle. But remember, we're only looking on a specific interval.
Maybe he took a shave.
between pi over 6 and pi over 3. So we're actually only looking between there and there, right? This is the interval in question. So are there any places on that interval where cosine is 0? No, none, right? Yeah, at 1/2, right? The nearest one would be 1/2, okay? So none. There aren't any, that first derivative, or that first type of critical number, aren't any on our interval.
So we'll just put none.
None, yeah, none. We're just making a list of them, because if we're finding absolute extrema, we're just gonna evaluate the function at all of the critical numbers and the endpoints and see what are the biggest and smallest values. Okay, what about the second kind? It's undefined. Yeah, when sine squared x equals 0. Well, where does sine equal 0? On the unit circle. 0 and pi, and 2 pi, and 3 pi, and just n pi, right? Are any of those on our interval?
No.
No. So we get no critical numbers on this one at all.
How'd you get your, this was just straight up?
Because that's given to us in the problem.
Okay. Alright, that makes sense.
Yeah, that's nothing you can ever calculate. That's just something that's gotta be established for you in the problem. Yeah. So there are no critical numbers. Yeah, so then if we want to find the absolute extrema, all we have to do is we're just taking the endpoints of our interval, right? We had one at pi 6 and one at pi thirds, and we're just finding out what are the values of the function there. So we know already that the highest and lowest points have to be the endpoints. Have to. There's only two things that could happen here. Either the function is increasing from left to right, or is decreasing from left to right. There can't be any turning points in between, no peaks and valleys, right? So if we do evaluate the function, what do we get? Let's see, cosecant, that's 1 over sine. So this would be, yeah, so it'd be 2. And this would be 2 over the square root of 3. So this would have to be, this is gonna be the maximum, right? And that's the minimum.
Yes.
Make sense?
Yeah, just grab it.
Wouldn't it be?
Did I get it backwards?
Yeah, I think it's
Sine.
1/2.
Oh, I got it backwards, didn't I?
Yeah.
I got them flipped. My mistake. That should be 2 over square root of 3, and that's just 2. Yeah, yep, you're right.
Alright.